Thank you, Dave, and it's my pleasure to be here at YOW Brisbane. I'd like to start with the story of deep dive performance analysis. This was a major microservice at Netflix, and normally we analyze microservices through a cloud-wide monitoring tool called Atlas. Atlas gives us 1-minute averages of metrics such as CPU utilization. We have another open source instance analysis tool called Vector. And since Atlas was so important, I'd moved to Vector to look at the instances for this microservice. This is a graph of per second CPU utilization for this microservice. And you can see that it varies. Sometimes we're at 80%, and sometimes CPU utilization drops down to 30%. This is interesting. Like I said, this is a very important microservice at Netflix. And it could be a sign of a performance issue. But it could also just be a sign of natural load variation. Netflix has many customers on the internet, and from 1 second to the next, there may simply be fewer clicks. So I'm not really sure. But it is quite interesting to have gone down from a 1-minute average down to a 1-second average. To get more information on this, I wanted to go down further. And I've called this before the 1-second problem of how do we drill down and visualize less than 1 second. Think about how would you do this if I said I would like to see this graph, this metric, in tenths of a second or 100ths of a second. Do you have a go-to visualization that would solve this problem? Many years ago, I created sub-second offset heat maps to solve this problem. It's only one solution, and you might come up with one that's better, but I'd like to show you how this works. Hands up if you've already used sub-second offset heat maps. That is one person, so you'll all get to learn something. What I'm doing is I am painting from bottom to top. Each column is 1 second. And when I get to the top of a column, I paint the next column from bottom to top. The color depth indicates, in this case, how many CPUs were busy for that time range. Time is on both axes. There's about 50 rows from top to bottom, and so the size of each of these buckets or pixels is about 20 milliseconds. This is great because I can now look at patterns within a second, and also in computing, things are often repetitive. Things happen at the same offset each second, and I'll see a line that spreads across this visualization. This was the result, the sub-second offset heat map for the microservice, and I could see that every so often there is these white columns that stretch for about 500 milliseconds. So what might they be? That's quite interesting because previously, when we looked at the line graph and we saw that CPU utilization dropped, we didn't know exactly what was going on. Maybe load was just lighter a little bit for that second. But now we have more information. Load isn't lighter. Load, in fact, goes to 0 for 500 milliseconds. Now I'm really interested in this problem because this really starts to sound like a performance issue. Looking at this visualization, the one I created, I can mouse over pixels and it gives me more information. And I discovered that for these 500 millisecond runs, the CPU utilization was not 0, but one thread was active, one CPU was active. Now this is getting even more interesting. So one thread is active, but all the other threads stop. That's an indication of perhaps a locking issue, where one thread is holding a global lock and a pool of thread workers can't make forward progress until it's released the lock. I looked at this using perf. That's our Linux standard profiler, and that's generating the samples. And browsing the output of what was running, I could even see it in text. The column I've circled shows the CPU that was active. And normally, because of interrupt latency, I will get these samples happening out of order across the many CPUs on the box. And so I'm sampling usually at, well, in this case, it's 99 hertz. So I'm not sampling in lockstep with some periodic activity. But instead of just seeing these samples come in at random order for each of those 99 hertz, I see CPU 19 is stuck on sample after sample after sample, and nobody else is running. I would think that CPU 19 is holding the lock everyone's blocked on. So I'd love to know more about what is CPU 19 doing. Another visualization I've created previously is called flame graphs, particularly CPU flame graphs. Has anyone used flame graphs before? OK, much better. So we've got like 20 people. I wanted to know this as a flame graph. I'll go through flame graphs later in this keynote. This was the flame graph I generated just for those single thread or single CPU runs. A flame graph is a visualization of profiled stack traces and explains the code responsible. And straight away, I could look at this and say, aha, we are in code cache cleanup. This is Java. This is the JVM. It is a microservice that had about 1 gigabyte of instruction text, the way Java was compiling things and compiling things and compiling things. And the code cache in Java was getting so large, it had to do its own garbage collect. But code cache garbage collect is not multi-threaded, it's single-threaded, and it's blocking the rest of Java. So this is definitely a performance problem that we can fix, and we worked on that at Netflix so that the code cache, there's various tunables that come with it, and also with the microservice, we were able to reduce the amount of code it had. That's great. That's an example of going from a line graph of 1 second CPU utilization right down to the root cause of those dips. But at Netflix, if I show this to other people, the reaction is, that's nice, but how do you get other people to do this as well? I accomplished this by SSHing onto systems. And at Netflix, we have so many instances, that's not really feasible for engineers. Instances come and go, they auto-scale. And so we're always interested in being able to share our skills. As an expert in an area, I should create a self-service GUI so that other developers can do this as well with mouse clicks. And so this became an internal tool called Flamescope that we have open sourced. And with Flamescope, we can go through the same process of clicking a starting and ending point, and then looking at a flame graph for that range. In fact, since it's so visual, and a lot of what I do is not so visual, a lot of what I do is Linux kernel internals and the command line, I would love to actually show this briefly. Here is a Flamescope, and I can see in this example, we have some activity that's waking up every second for a little bit of time and then going to sleep for a full second and then waking up again. It's creating these diagonal lines. What might that be? So again, on the y-axis, I've got the sub-second, and each column is a full second, and then I paint the next column. I see these diagonal lines. That's a case where the programmer has said, do some work, and then sleep for 1.0 seconds, and then do some work again. And what happens is you end up waking up at a progressively later offset each second. If instead you set up a high-resolution timer to always wake up at the same offset, you get a horizontal line. There's some other patterns visible in here as well. I have some perturbations on the right. And with Flamescope, we can click on any of these. So I can just click on the background, what was happening over here. And then I get a flame graph that shows, in that case, we're doing, that's right, this particular Flamescope, I was looking at the startup of a microservice. We wanted to take the startup time from 10 minutes down to 1 minute if possible. And so early on, we are doing OS pre-touch memory. Java is creating its heap, and I can see that. But I could also click on these perturbations, like over here, just that, and say, what is that? OK, at that point, the application is running, and we're starting to do some garbage collection. So you can imagine you can navigate a profile. These are flame graphs. I'll explain them in a moment. You can navigate everything that's going on. And since I've always wanted to do this, we added a button called Enhance. Wow. All I'm doing is I'm setting the palette for the very low samples to be blue so that they pop out. But you can now see that there's actually, this is the JVM starting up, pre-touching memory, so it's allocating its heap. And now we're starting to run the application. Here's our garbage collect kicking in. We've still got this diagonal line, and I can debug that by just clicking on it. Let's click on one of these. And if you look closely, you see awk, chown, run. This is a shell script that's actually doing a sleep 1 and then doing some shell commands. It was actually a misconfigured start script that was trying to do something, failing, and then sleeping for 1 second and trying again. So I can disable that and get some CPU cycles back. So that's Flamescope, and sometimes, oh, that's just perturbations. Sometimes there's very interesting patterns that you can browse and explore, and they pop out in ways that they would not in line graphs. There are 3 factors for successful root cause analysis in an environment like Netflix. There's observability. There's having access to the metrics and the stack traces and the symbols so that we can do things like this. In this case, when I started at Netflix, we couldn't run a system profiler on Java because Java didn't have the frame pointer, and we couldn't walk its stacks, and that's now been fixed. So we can do things like Flamescope, where we can analyze Java and Node.js and other languages as well. There's methodology, which is what do you do now that you're given all of these metrics and information. And the final one is velocity. And velocity at Netflix is about developing features as quickly as possible, getting out of the way of the developers, empowering the developers to be more effective and faster. And whenever I work on the performance and operating systems team, whenever I develop tools that go deep, it's then about enabling the other developers. How can I create a self-service GUI so they can do it as well? This keynote is about root cause analysis at Netflix. I've drawn a diagram to show the Netflix stack and various tools I'll summarize. This talk is about exposure. You aren't expected to learn all of these tools, but it's helpful to know that they exist. And then sometime later you might think, there was a tool, I saw this keynote by Brendan, I can look up the slides online and remember what that is. Practically everything I'm talking about is open source, and so you can read about them, and you can fetch the source and run it yourself. This is 4 talks in one. I will summarize the Netflix cloud. I will talk about methodologies. I'll then do cloud analysis and show you the tools we're using right now at Netflix, and then instance analysis. I only gave this talk once before in 2014, and there's an old screenshot of Atlas, our cloud-wide monitoring tool. That's changed, and so has many things. So we've moved from Asgard to Spinnaker for doing cloud deployments. Our internal tool, SOLP, we're now rolling out Zipkin. We're starting to adopt gRPC, and so on and so on. The last 3 I worked on myself, the Java Frame Pointer, eBPF, and PMCs. And I'm excited to be able to share some of the things I did with you. To summarize Netflix, who has Netflix? Who has Netflix at home? That's pretty much everyone, so thank you very much for being Netflix members. We have a very large EC2 cloud, over 150,000 instances, and we're hitting 34% of the US internet traffic at night. And we have over 130,000 members. Performance is critical at Netflix. It's about customer satisfaction, so that when you log in, you're using the interface, it's fast, there's not buffering. And it's also about Netflix cost, so that it's not too expensive for the rest of Netflix to be running all the wonderful things we run. These slides will be shared online, and I have a slide in there for the acronyms in case I don't explain them. So the first section is on the Netflix cloud. Just to summarize this, we're deployed on EC2, I mentioned that. We're also using Elastic Load Balancers and S3. On EC2, we have a lot of Cassandra, Elasticsearch, EV Cache, and of course the applications, which are microservices. The microservices we have include authentication, user data, personalization, viewing history, and there's 2 main APIs the client devices access them from. We also have, apart from the Amazon EC2 Cloud, we also have a CDN called the Open Connect Appliance, which are physical boxes running FreeBSD. When you first log into Netflix and browse around, you're coming from the Amazon EC2 Cloud. And when you hit play, you're coming from a physical BSD box that's hopefully very close to you, that's at the ISP. We have a culture of freedom and responsibility. The culture memo is true. It used to be a deck that's had 18 million views. And for developers, you have development freedom. You can purchase and use cloud instances without approvals. You can try out new technologies and prototype them. It makes my job at Netflix exciting because there's always new things people are trying out and they want my help with to do performance evaluations and analysis. The cloud technologies that we use, they're usually open source. So Linux, Java, Cassandra. We also write and publish things ourselves. So on netflix.github.io. Here's an idea of a typical base AMI instance. The microservice teams can customize them, of course. And so some of them don't run Java. They're running Node.js or they're running Golang. But a typical one would look like this with Linux, Java, and various standard things that we ship with it. For root cause analysis on the bottom left, that includes things like ftrace, perf, BCC, and eBPF, and I'll summarize them later. Another way to understand Netflix is to go through 5 key issues and how the Netflix cloud is already architected to solve them. The first is load, if load increases. We're using auto-scaling groups. A lot of you may be already doing this. So we have a custom scaling policy that might be based on load average, CPU utilization, latency, and that can automatically add instances as load increases. This is great for customers because if there is a load increase, then we're already deploying the workaround to improve performance. It's also good for engineers since if there is a load increase in the middle of the night, Netflix can often auto-scale itself out of the problem. And so as an engineer, that may avoid getting paged. And so you come into work the next morning at 9 o'clock and then you deal with it. Netflix has paid a bit more money to auto-scale up, but all the engineers have got to sleep through the night, so that's a great thing. Another important aspect is what happens with a bad push. So we have red-black auto-scaling groups, and we're always rolling out new software versions as a new auto-scaling group, and then we'll use the elastic load balancers to slowly siphon off traffic from the current active one to the new one, while the engineers are looking at metrics and dashboards. And if things look bad, they can simply roll back to the old ASG. Those instances are still there, they're warm, Java's still running, the heap is allocated. But if things look okay, they can keep moving the traffic over and then eventually shut down the old ASG. We can also use canaries and automated canary analysis to create a single instance and then see how that performs. Instance failures. We have Hystrix for timeouts, plus many, many other features, and also Ribbon, which is our internal tool, or gRPC, which provides more redundancy. If something bad happens to an instance, and I've done this myself at Netflix by accidentally panicking instances, it's not a big problem. The requests that have gone to that instance automatically time out higher up in the Netflix cloud stack and go to backup instances. So as a customer of Netflix, you may have a 100 millisecond latency as you're browsing the UI. You may not notice that. But what's happened is an instance has been terminated or has panicked or something very bad happened. So it's a fault-tolerant architecture. We also survive faults at the region level or the availability zone level. And we've got Zool2, which is our proxy. And we can redirect all traffic from one region to another. And we simulate this many times so that we can check that everything works. That simulation is part of chaos engineering, which is the last key part of the Netflix architecture of why things work so well. With chaos engineering, we have software that will automatically terminate instances. We'll simulate availability zone failures. We'll simulate high latency on dependencies. As a developer, you have to write your code to deal with these situations because they will happen. And if you don't believe it will happen, when you start deploying applications, it happens. So it becomes a reality real quick. And so when I joined Netflix and I started deploying my own applications, I was manually setting things up, and I'll just SSH on and do this config file. I haven't really saved it in the right repositories, I know, but it should be OK. And then you get the email saying your instance has been terminated by chaos engineering. And it's like, wait, I should have saved my config. I should have done all these things. So quickly you learn that you have to take this seriously, and you have to design your application to be fault tolerant. So you learn that the hard way. So I've redrawn that diagram of the Netflix stack, and here's I've highlighted in bold the areas that make us fault tolerant. So elastic load balancers, auto-scaling clusters, auto-scaling groups, availability zones, and at the top of the stack, the different libraries we can use to provide fault tolerance as well. In the second section, I want to summarize methodology. Like I said earlier, it's great to have access to all the metrics, but the problem then becomes, what do you do with them? To start with, why do we do root cause performance analysis? High latency is a common reason I get pulled into doing this. With high latency, there is some logical issue, and auto-scaling often doesn't work. It is a type of issue you can't auto-scale yourself out of. So with high latency, often we do need to get to the bottom of it. Growth, or cost at Netflix, is another reason we want to do this, so that our costs don't get out of hand. And also upgrades. You can't stay on the same Linux kernel version forever. You can't stay on the same Java version forever. You can't stay on the same Cassandra version forever. And with new versions, often performance regresses because they've changed how things are configured, and you have to update your configuration file. Or maybe there's just a software regression with the new version. And so that's another case where we are often doing root cause analysis because we know we need to upgrade to the next version, but it's 10% slower, so we'd like to identify why and work with the developers and get that fixed. For cloud methodologies, there's a number you can use. One of them is resource analysis, and that's where you check if any of the physical instance resources are exhausted, like CPU, disk, and network. There's metric and event correlations. Dashboards are great for this, where you're putting the same time series over top of each other, and you try and see when latency went up, what else happened. There's latency drill downs. I'm looking at my application request. I want to decompose it into the wait states, and then keep drilling down until I get to the bottom, the root cause of why that application request was so long. And the last one I've put there is the RED method. That's microservice focused. And that's a great methodology where you list out your microservices. And you say, for each microservice, I just want 3 metrics: the rate, the request rate, the errors, and the duration. And you can imagine you can create a RED method dashboard where you list your microservices and you have those 3 key metrics. We're often drowning in metrics. There's many, many metrics. So having a methodology that whittles it down to 3, but also encourages you to not overlook anything is really useful. So you make sure you do have RED coverage for every microservice. Going down to the instances, log analysis, micro benchmarking, drill down analysis. A methodology I came up with a while ago is the use method. And that's where you draw a functional diagram of the system. CPUs, memory, disk controllers, network controllers, disks, all of the components where data flows, including the buses. And then for each of those components, you only want 3 metrics: utilization, saturation, and errors. Again, this is a useful methodology because you don't have blind spots. Instead of just consuming what the system gives you, it's posing questions you ask of the system. And also, it is whittling it down to just 3 metrics for each of those components. Now, I've caused many issues because I'm reminded to go and check the buses and discovered that we have a memory bus saturation or CPU interconnect saturation. And finally, just as an example of a anti-methodology, the bad instance anti-method, This is something I see from time to time. I can understand the motivation for doing it. That's where you have an instance that has high latency, and you think, I'll just terminate it and hope the problem goes away. And so sometimes that might be cost effective, but I just want to remind people that can be an early warning of a bigger issue. And so it can be helpful to root cause these whenever possible so that next time this happens, it's not 10 instances instead of 1. Now I'll summarize the cloud analysis tools. Since I'm going to go through many tools that we use at Netflix, I've drawn this flow diagram or a mental map to show how they fit together so that we don't get too lost. And again, this is just for exposure. You may be doing very similar tools. I might mention a tool you don't have something for, and so that can be a gap that you might want to explore. And so we often start with Atlas alerts, where it will give us an issue that we need to investigate, and then we start going through the other tools. The main metric we alert on at Netflix is streams per second, and that is how many times members are hitting play. This is a daily graph of streams per second, and it follows a certain pattern. And if that deviates even by a small, tiny amount, it will create alerts. So there's a tiny deviation over here, that's almost certainly created alerts, and then I get them in my mailbox. These are my Atlas alerts. It's a little hard to read here, but I can show you the makeup of an Atlas alert. This is one from a few days ago. So I'm showing you the very latest Netflix internal tools, how they look like right now. We start off with a new tool that we've developed called Winston. There's a Netflix tech blog on it for automated diagnosis and remediation. And that can look at an alert and can say, maybe it's related to this fast property change, or a new ASG has been deployed. It has programmable runbooks. And so our core SRE team and other teams were following the same mental methodology when alerts were happening, and this is a way for them to program it and then get that in the email. Kronos is our event logging tool. These are possible related events, and then links to Atlas dashboards. And Atlas dashboards and metrics lets us drill down. It's really great to get the actual PNGs in the email, because when you get this alert, you may not be connected to the Netflix VPN, and it might take you a minute to connect to the VPN. And in that minute, you can start looking at the graphs and start mentally working on the issue. And then you connect to the VPN, and then you can click on the links. So it's great to get those images in the email. Many of them will link to dashboards. We make every service team has dashboards, make big use of dashboards. Here's an example of the Netflix Performance Vitals dashboard, where we go through different metrics. That's one I tend to use a lot. Dashboards themselves are another example of a methodology, a checklist methodology. Because when you're building it, you're choosing, what am I going to show people first? What am I going to show people second? And you're making that evaluation of what's most important and what's the sequence you want people to look through. We've been developing a new, more flexible dashboard approach, a tool called Lumen. And there's a Netflix tech blog on it that showed that they've got a Lumen dashboard to tell us when it's burger day in the Netflix kitchen. So you can go to go/burger. They can do more things than the older Atlas dashboard. Metrics looks like this. So there's ways to select the application, the metrics I want to view, the presentation, sum, min, max, average. And then I've got my interactive graph. Our Atlas metric system is one of the largest microservices we have. At one point, it was reaching to 10% of the Netflix footprint, which is a little bit amazing to think about. It means that for every 9 or 10 instances you deploy, you have to deploy one more instance just to monitor the other 9 or 10. And the reason is Atlas is storing millions and millions of metrics in memory so that we can pull up these graphs for anything. I want to pull up this graph for SPS for this region, for this application, for this device type, and it's immediately fast for this time range. And we put all the metrics in one system, system metrics, application metrics. Chronos is then how we communicate changes that have happened. So I can select my scope, time range, event log, and then I can filter. So the GUI is interactive. I can quickly filter down and just look at events that are most interesting. We've debugged many issues just from Chronos because you can pull up the event that's caused the issue and the times line up. So very important, and all service teams need to publish through Chronos. So a really great tool. Slalom is our tool for doing dependency graphing. And here I've got an application, and you can see the flow of traffic going to dependencies and their dependencies and so on. And the traffic volume. This used to be based on the Netflix SOLP, which was our dependency tracer, but we've now switched it to be Zipkin based. And Zipkin has its own UI, so that we can look at dependency latency as well. And the final internal tool that we've developed is Pixo. That's for AWS usage. And the other tools are great for customer satisfaction, resolving latency. This one is for Netflix cost, so that we can understand our cost and growth, and then target resources to where applications are growing. This is the slide I've had to redact the most. So I've had to put gray boxes on it because it actually has the Netflix Amazon bill as part of this UI. So quick way to find out where that money is going. There is one more tool, although we didn't develop it, and that's Slack. And I used to be I did some SRE on-call for Netflix, and I found a quick diagnostics methodology was to say in Slack, in the main core chat room that everyone looks at, latency is high in this region for this service. And quite often the engineers would then confess and say, oh yeah, that's my fault. I pushed a change. I'll roll it back. So it turns out just communicating with everyone can be a great diagnostics tool. So there's the Netflix cloud analysis process, including Slack. And I've redrawn it so that it's generic. So you can think about how that might apply to your environment. Instance analysis. Now, these are the tools we use to understand an instance. I've drawn a generic diagram of the Linux kernel so that I could decorate it with all the tools that we can use. I forget these tools, so I have this printed out on my wall at work so I can refer to it myself. And if I'm using these tools to solve problems at Netflix, it then becomes a problem of velocity. We don't actually want engineers SSHing onto instances to run all of these Linux tools. We want to then turn it into a GUI, a UI, that engineers can click on that's self-service. The first one to mention is statistics. And VMstat, PIDstat, SAR, and so on, these work mostly normally when we run them in the EC2 cloud from the host. And if we can't see something because it's in the hypervisor or as part of the network, we can do some micro-benchmarking to get information. There is an exception to Linux statistics, and that's containers. Currently, the Linux kernel performance tools are not all container aware. So if you run tools within a container, some of them are showing you just the container, and some of them are showing you the full host. It's getting better. There's always lots and lots of work happening in Linux. C groups are adding metrics. So over time, we'll get to the point where you can log into a Linux container and run everything, and it will be scoped just for that container. But at the moment, be aware that that may not be the case. We work around it at Netflix by, we have an agent in the host, and that agent is reading C group metrics, and we expose it through our vector UI so that we can look at per container metrics. But I just wanted to mention, if you log into a container and run VMstat and top and uptime, it's not a given that all the metrics are going to be scoped for that container. So I've mentioned vector a number of times. Spinnaker is our main deployment tool. Anyone using Spinnaker? So some people. So we go from Spinnaker, I can click on Insight and go straight to vector, and I'm looking at a particular instance. Profiling. I'll start with a story. This was an issue I worked on where the microservice team said, ZFS is eating my CPUs. I worked on ZFS at Sun Microsystems. I worked on the code and also performance analysis. And I don't think ZFS is eating your CPUs. I did a lot of work on ZFS, and this is probably not the case, but I'll help you out anyway, and I'll check it out. So to prove to them that ZFS was not eating the CPUs, I thought I would create a CPU flame graph, which I'll explain in a moment. And the CPU flame graph looked like this. The application, I've colored Java in green, and then kernel time I've colored in orange. And with the kernel time, I can see, wait a minute, we are in ZFS. We've got SPL, and we've got the arc reclaim. They're actually right. We are in ZFS. ZFS is eating the CPUs. 38% of kernel time is eating the CPUs. Oh, I know, this is a misconfiguration. It's not that ZFS is doing anything wrong, it's because I bet they misconfigured it. I bet they're using a small arc record size, and it's trying to do arc reclaim, and it has to walk through metadata that's huge. That's why. So I tell them, OK, you're right, ZFS is eating your CPUs, quite a lot of it, 38% for the entire system, but it's because you've misconfigured it. I bet you've picked a small arc size. What they told me was even more surprising. They said, we're not even using ZFS. It's like, I don't think so. You are using ZFS. The kernel doesn't just eat CPU because it feels like it, because it's hungry. You are definitely using ZFS. I can see that you're using ZFS. So I thought, I know, I will log into the instance, and I'll pull up the metrics, and I'll prove to them with beyond a doubt that they are using ZFS. And I go into the proc/sys/arcstats, and it was true. They were all 0. They weren't actually using ZFS. So what the heck is going on? So I can zoom in with the flame graph and have a look. And looking at the arc reclaim thread, and I'm familiar with this, I worked on it. The arc is the adaptive replacement cache. That's the main file system cache for ZFS. For reclaim, it is cleaning up memory. And it's picking, it saves memory in different lists. And it's choosing which list to free memory from by get random bytes and extract entropy. It turns out there was a ZFS change where instead of doing a round robin through the lists to free memory, the engineer thought, wouldn't it be cool if we picked a list at random? But I don't mean simple random, I mean like really random. I mean like really cryptographically secure random. And so 38% of system time is because ZFS is deciding which empty list to free from using the most secure cryptographic random algorithm. So I filed a ticket with ZFS and to get that fixed pretty quick. So if the lists are empty, don't iterate through them to free them. There's nothing to free. So it should be an easy fix. It's an example of CPU flame graphs are great and profiling is great because you can quickly exonerate or prove issues and hypotheses and see what's really going on. When I started at Netflix, CPU profiling looked like this. There were Java profilers that let me look at Java and system profilers, but Java was all broken because we couldn't look at their system stack trace. And the reason was that Java did not honor the frame pointer, and that's how system profilers typically walk stacks. Java used that frame pointer for performance optimization that made sense many, many years ago, but doesn't really make sense today. I worked on OpenJDK, and I came up with a patch to fix the frame pointer. Oracle were nice enough to take that patch and rewrite it and get it included, and that's now the preserve frame pointer option. And now we can do mixed mode flame graph so we can see Java and we can see garbage collect, I can see the JVM kernel. I'm coloring different code types in colors to make it easy to browse. So CPU flame graphs, I've zoomed in a bit. Since most of you said you hadn't used them before, I'll explain how they work. The y-axis is the stack depth. The x-axis is just the passage of, the x-axis is just the population, all of the samples. The x-axis is not the passage of time. The x-axis is actually the alphabet. And I picked the alphabet so that I could reorder samples and then merge the frames more easily. This is what happens if I use the passage of time on the x-axis. So you end up with hair and grass, and I can't really read the frames. There's one exception that gets away with this, and that is if your application is single-threaded. Like the problem here is the application is multi-threaded. The samples, they're doing different things. We can't merge the boxes. An example of a single-threaded application is V8 in Chrome. And so in Chrome DevTools, they use this. They call it flame charts. And they do have the passage of time on the x-axis. And they kind of get away with it because it's single-threaded. Since I'm working on multi-threaded systems, I need to use flame graphs, where I throw away the passage of time and I just have the alphabet to maximize merging. So to read them, if this was my sample flame graph, the top edge is what's on CPU. So I'd see that function G was on CPU the most. Function E was on it a little bit. I was on a little bit. A fraction of D was on CPU directly, a little bit, but its children were also on CPU. And the y-axis is the stack depth. I've summarized flame graphs in one slide. So 0 is at the bottom for the stack depth. Some people like to flip them and put them upside down, icicle graphs. If the x-axis is time, that's a flame chart. And so I've colored there. That's who's running on CPU, is the top edge. Our primary approach for doing application profiling at Netflix is these CPU flame graphs. Mixed mode flame graphs. It's important to see the kernel as well, like when I was debugging that ZFS issue. Because there are many application profilers, but they only show you the application content. You may need frame pointers for this to work. You may also need a supplemental symbol file. If you're doing flame graphs on Node or Golang or anything, if you do an internet search, you'll probably find someone's posted the instructions, or I've posted the instructions. And if not, figure out the instructions and then post the instructions so that other people can find them. If that doesn't work, we will then use application profilers or application logs. But our preference is push-button flame graphs. We have them in vector so that you can say, start capture for 20 seconds, CPU flame graph, and then I'm looking at it straight away. The way flame graphs are currently generated looks like this. On Linux 2.6 onwards, we would run perf record. That would write to a perf.data file. Perf script would process it. I would then run it through stack collapse to summarize those samples, and then flame graph. It's a little bit inefficient because we're writing to the file system, we've got CPU time, and we're dumping every sample out. A more efficient way is coming in Linux 4.9 onwards, and that's a new tool I've written called profile.py, although it's based on code by many other people. And that's able to summarize, sample and summarize stacks in kernel, and just write the summary straight out so that flame graph can consume it. So I just want to mention this because flame graphs are going to become even cheaper to run, and they should be even more commonplace. Profiling actually solves, I would have to say, most of the performance issues at Netflix, CPU profiling. And part of the reason why is we're deploying changes so often. And so developers can bring up a CPU flame graph and see what happened. To get down deeper, there is tracing. I'll explain these, but I want to preface with the following sections get into software and hardware very deep. You should think about that as I'm showing you an X-ray machine. You don't all need to know how to operate an X-ray machine. You just need to know that it exists so that if the time comes, then you either learn or you find someone who knows how to do it. If I fell off this stage and broke my foot, and then I was walking around thinking, my foot hurts. Oh, my foot really, really hurts. You'd all probably tell me, go and get an X-ray. And that's what I want to get to you with these tracing tools and hardware tools, so that you know that if that time comes and your application stack breaks its foot, you then go and find the tool. Tracing itself in Linux has been really difficult to understand and get our head around because there's been so many different tracing tools. My partner, Deirdre Strawn, who does many things, amazing things in technology, has also drawn ponycorns for each of the Linux traces. And some of them have been adopted as the official mascots. And so we've got the ftrace ponycorn, perf, eBPF. We have too many traces. This has been a big problem in Linux for a while. We have so many ponycorns we can make a really terrible children's show on the driest topic ever, Linux tracing. Just to summarize it, what I like to do is to say what Linux traces are in the kernel, a core that are available. And so they are ftrace, perf, and eBPF. All of the other ones are add-ons. ftrace and perf have been around for a long time, so you should have access to them. ftrace has these great custom tracing views. eBPF is the newer technology. It's a programmatic engine, and we've been adding complex tools and short scripts using a couple of open source projects. To explain how these fit together, here's an example issue. The service team told me their disk became busy. Our disk busy went up to 80%. What's going on? This is a screenshot from Atlas. Okay? So I log into the instance and have a look using IOStat just to confirm it. It's true. Their disk is 87% utilized. I want to know more information. Let's drill down further so I can understand what's causing it to be busy. This is a perf-based tool using one of the older traces, and it's showing me a latency distribution where I can see that we have two modes of latency. One mode is 0 to 1 milliseconds, and the other is 8 to 16 milliseconds. I see this all the time for disk analysis. The first mode is cache hits, and the second is cache misses. This doesn't actually look that unusual. This just looks like a problem of load then. I don't see any ridiculous outliers. I don't see modes in a place I'm not expecting them. This is normal for, say, a 7200 RPM disk. So this points to a problem of workload, not the problem of the hardware. I then used another tracing tool. This is like TCP dump, but for disks. It's another one I wrote. And I can see that Java is doing these, is applying the disk I/O. I can see the latency for each of them. But just by getting some more information, just like you do when you TCP dump and you're not sure about an issue and you just want to see if something stands out, something did stand out. These were metadata I/O. Metadata. I had not, well, I think M stands for metadata. This is actually this field called RWBS in the kernel. And the kernel actually saves it as the character string. And I'm just fetching that character string and printing it out. And I kind of forget what the characters stand for. I saw there was a thread once on the internet where someone was asking about what do the letters stand for and what does M stand for on this and that. And I thought it'd be helpful, and I'd reply, and I'd say, hey, it's not documented. You have to read the kernel code to understand what those characters mean. They replied to me and they said, no, it is documented. It's in the man page. I thought, well, I feel like an idiot. I should have read that man page, huh? So it actually was documented in the man page. I was like, all right, thanks for that. I guess I should have read it. Which man page? Which man page documented this? Because I swear I've never seen this documented in the man page. So I go and find the man page. I wrote the man page. It's my own man page. I've written so many tools, you do forget from time to time. So then I felt really embarrassed. Like, all right, so I have actually documented these before. Metadata. So I can trace just the metadata using perf, and I find out that, so now I'm going to trace when we're doing metadata disk I/O, show me the stack trace of who's causing it. And it's all this stat stuff, stat. And it's coming from Java. And it turns out that they had installed a new app called Disk Usage Monitor to find out the usage of their application. And that Disk Usage Monitor was just calling stat all the time in a loop. So Disk Usage Monitor was also Disk Performance Problem Creator. So I said, why don't you turn it off? And like, this new app you've installed. So they turned it off and the problem went away. So just as an example of using some tracing tools to understand what's going on, as an example of a more modern tracing tool, here's BioSnoop, which is from using eBPF. It's similar to what we saw earlier, but the point I want to make here is it's more efficient. I'm doing these latency calculations in kernel. That's using eBPF. eBPF. Who's heard of eBPF? So a few people. It is extended Berkeley packet filter. At the Linux Plumbers Conference recently in Vancouver, there were 24 talks on eBPF. It is becoming huge. What it is a virtual machine technology. It's really like superpowers. It's a virtual machine technology where in user space I can define a program, and then the kernel can run that program. Previously, anytime you wanted the kernel to do something fancy, you either had to modify the kernel code or write a loadable module. Now, if you come to Netflix and you're trying to sell me some application you've written that requires a root daemon or a loadable module, we get a bit nervous about that because your code could crash Netflix. With eBPF, however, if you write your application in eBPF, it's running in a virtual machine that's sandboxed and known to be safe. So now when people are trying to sell me some product they've developed, I tell them, is it eBPF? It needs to be eBPF. That's the sandbox machine. eBPF is being used for many things. It was originally developed as a software-defined networking technology, but it's being used for DDoS mitigation, intrusion detection, container security. I'm using it for observability. And it can take events from many sources and then run a mini program when that event happens. I've been developing many eBPF-based performance tools. So another one of my diagrams where I've been writing all of the performance tools. The point here is like, yes, we have this amazing X-ray machine, so you can see inside anything you want. If you thought you had a problem with virtual memory, or if you thought you had a problem with TCP or VFS, there's probably a tracing tool that will give you more insight. And BCC, here's one of my favorite tracing tools. The idea of this came from Julia Evans, who said, I want a tool that just, I can say, show me who's connecting to this port, like which application is connecting to the port. This is really efficient. It's not doing packet tracing. I'm just tracing when TCP connections are established and when they close by tracing those kernel functions. And then I'm doing a summary where I'm printing out the process, the IP addresses, how many kilobytes were transferred, and the duration. So it lets us write these new great tools that are also efficient and production safe. And I wanted to mention there's one more called BPF Trace, apart from BCC. BPF Trace is a new one we only launched a month ago, which you can write the similar tools, but the source code is very small. It's a high-level language for doing tracing. Again, whenever we're looking at this, if I showed this to other people at Netflix, they would say that's great, but it needs to be a self-service GUI. So in the future, many of these eBPF things need to be self-service GUIs. So there's an example from Linux when we were developing this, which has a latency heat map. So I can identify multimodal latency and outliers, and that's based on eBPF. It's efficient. The last deep dive tools I want to mention for exposure is processor analysis. And this is becoming the #1 performance problem we're exposed to. That is, if you see the CPUs are 90% busy, you might think they're busy and then they're waiting, idle, for 10%. What it typically means on the Netflix cloud is most of the time is waiting stalled on stall cycles. And the reason is that CPUs, the clock speed has become very fast. They've added more cores and hyperthreads, but the memory subsystem has not been scaling as fast. And so now we're just blocked waiting on memory. And when the instructions are blocked, they call it stall cycles, where the CPU is not making forward progress. To debug this, when I started at Netflix, there was no way to debug this because we didn't have performance monitoring counters on the cloud, and that's what you need to get information out. Recently, Amazon have been turning them on. And so for the Zen hypervisor, for the very large instances, you get the architectural set, which is great. There are hundreds and hundreds and hundreds of PMCs. This is just 7 that they've turned on for those instance types. I also believe PMCs, they're such a narrow, deep topic, I don't think Amazon has documented them. So this is an undocumented feature on EC2. The documentation is my slides that I'm showing you. So you can use these, in particular instruction retired and reference cycles, let you calculate IPC. IPC is instructions per cycle. If you haven't encountered this before, it's similar to like a miles per gallon. Miles per gallon tells you how efficient, what are you getting out of the gallons you're putting into a car. Actually, I'm in Australia, so this is going to be kilometers per litre, kilometers per litre. Phew. So kilometers per litre. And with IPC, it's the instructions we're getting out of these cycles that we put into the CPUs. You can actually go beyond 1.0 because we have a superscalar architecture, and the CPU decomposes instructions into micro-ops and can retire more than one at once. So we can actually go up to 4.0 on a 4-wide processor. But just to give you an idea of a spectrum, if you're over 2, that's good. You're retiring instructions really quickly. If it's less than 0.2, that's really bad. You're stalled on main memory. You should be measuring IPC along with other metrics, along with percent CPU utilization, so you can understand where you are on this spectrum. And if you are down at the bad end, then instead of buying faster processors, you should be looking at memory, how you're dealing with memory, how you're using memory. Can you use less memory? Can you do zero copy, and so on? That's how it looks like to measure it using perf stat. So I can see my instructions per cycle. I also wrote a tool called PMC Arch, which prints it out line by line for IPC. And I want to mention in the new Nitro hypervisor by Amazon, they've enabled many more PMCs, which is great because I used them for doing the translation look-side buffer analysis for the Meltdown KPTI patches that Linux had to include. And so I can see we're spending so many times in stall cycles for data and instruction TLB page walks. It's great to actually, when people tell you may have heard earlier in the year when those patches came in that Linux could run much slower because of the security effects. We can actually measure it and we can see it. We can quantify it for our workloads. It's great to have that low-level insight. And the last low-level insight that I like to use is MSRs, model-specific registers. That's an example from an instance that we debugged last week where the megahertz was not running as fast as it should do. It was supposed to be running at 2500 megahertz. It was actually running at 130. And the other Netflix engineers showed it to me. It's like, because I wrote show boost. This is a great tool, Brennan. You've debugged this issue. I'm like, have I debugged this issue? That is so low. I wonder if there's a mistake in my tool. The CPUs shouldn't be running at 130 megahertz. So we did some other debugging, and it was actually true. So there was a problem with that instance, which we got fixed. So more insight, just double checking that the clock rate is running as it should. In summary, so I've given you exposure to many different tools, but if there were 3 takeaways, I would say that's CPU flame graphs for looking at all the cycles, where it's going, and make sure they work for kernel and user space. Check out the eBPF perf tools. You'll be hearing more about this in the future. Particularly at Netflix, part of my job is to now build UIs on it to enable other engineers to use it quickly. And of course, we open source pretty much everything we do. And for CPU utilization, you should be measuring IPC as well so that you can understand what that is, whether it is instruction bound or stall cycle bound. I began by saying observability, methodology, and velocity. And I think we're in an exciting stage. When I started at Netflix, we didn't have eBPF. We didn't have PMCs on the cloud. Now we have all these things. So you can come up with great methodologies and some great new GUIs so that we can use them and root cause analyze our systems. These slides will be online, and I've got resources. And there's also the Netflix Tech blog, which is a great resource for what we do. And thank you very much.